Okay, so hello everyone, and I would like to welcome you all back to another installment of the online 3D Geometry and Vision Seminar. My name is Angela Yao, and I'm an assistant professor at the National University of Singapore, and I will be your host today. And it is my great pleasure to welcome our speaker today, who is Professor Gao Ling from the Institute of Computing Technology at the Chinese Academy of Sciences. Professor Gao works in the areas of geometry learning, mesh processing, and 3D computer vision. And today he's going to talk to us about deep generative mesh models. With us today are also two panelists, Mo Kai-chun from Stanford and Professor Yi Li from Tsinghua University. So without further ado, I'd like to hand over to Professor Gao to start his talk.
Yes. Thanks a lot. Thanks for the invitation, and thanks a lot for Angela's introduction. And now we will begin the talk. The talk title is the 3D deep deformable generative mesh model with geometry and texture. Now let's first review the brief history of the multimedia processing. And the multimedia processing is from the 1D data to the 3D data. From the voice to image, from the image to video, and from video to geometry and to the dynamic geometry. And the application of the deep learning shares the similar history. Also, the deep learning firstly has been applied to the voice or image processing, and then has been applied to video, and also has been applied to geometry. And in the next, the challenge of the multimedia processing is the high-dimensional data, such as the dynamic geometry or the 3D model with complex topology and detailed geometry. And this 3D model are quite challenging for the deep learning, especially for the generative model. And if we look at the property of the 3D model, they could be disentangled with these properties. So look at the mesh models. They are usually with complex motions, such as humans and clothes. There are some complex motion behind the 3D model, and they bend the physical rules. And also for the 3D model, there are very detailed geometry. The geometry details are very important to the 3D model. And also compared with the image, there are also another thing of the 3D model is the structure. The structure is usually also very complex and not easy for learning method to handle. And besides this, there are also another thing is quite important for the visual quality is the texture. So if we look at the 3D model, there are several properties behind the 3D model. So if we want to generate the 3D model, we need to analyze and generate these properties, that including the motion, the geometry detail, and also the structure and the texture. So firstly, let us review the history and the related works of these research works. So for the motion or deformation, there is one very important application is to reuse the deformation to generate new mesh deformation. Like this task. This task is named Deformation Transfer. The aim of this task is to transfer the deformation from the source model to the target model. For example, there is the motion of the cat, and we want to reuse the motion or deformation of the cat to deform some similar mesh model, such as a dog or something like this. And there are many famous work to solve this problem. Usually for the traditional method, they will use the human effort to label some mask. And this mask will be used as the handle to transform the deformations. Usually, they will reuse the deformation gradient of each mask, and then to use the boson reconstruction to field the transformed deformation gradient. I think this is the key idea from the previous state of art method. So there are a lot of works for the human. They need to label the correspondence between the source model and the target model. For example, like this figure, there are two human motions. They need to label the correspondence between the two mesh models. So this is the solution for the deformation transfer for triangle meshes. This is the paper from the CRAF to 2004. And the next, there are some much advanced methods. They need to make the correspondence not between the mesh vertices, but they make the correspondence between the mesh model itself. Like this work, this is the CRAF 2009. This work is used to the pair of the models to make the correspondence. So it's not to define the correspondence between the vertices, but to define the correspondence between the different objects. Different mesh models will build a deformation space, and then they will make the correspondence between the different mesh models to make the pair. So all of these works need the human effort to label the correspondence. The correspondence is either defined on the mesh itself or on the mesh vertices. So there is need some human effort to make the correspondence. So it's not an automatic manner. But with the deep learning, we design an unsupervised method to transform the deformation, and which we would introduce in this talk later. So, and if we want to reuse the deformation in the automatic manner, we need to analysis and encoding the deformation, to do the encoding and the decoding of the deformation. And also we need to develop some deformation representation to represent the human motion. And also we need to develop the encoder to analyze the motion. And next, we need to develop a network to automatic learn the correspondence without human effort. So this what we would talk in the first work. And also another very important task in the 3D mesh processing is the mesh reconstruction or mesh modeling. So this is another very important task. And in recent years, with the development of the generative model, we could do the mesh modeling with the deep generative model. But it's not an easy task because the mesh model is with very complex structure and a very detailed 3D geometry details. So this is different, very different from the 2D images. So there is very pioneer work, such as the Kashan and Edith work to model the 3D model with the point cloud representation. They use the point cloud to classification and segment the 3D model. And also they are using they also use the point cloud to generate the 3D model. And also there is something similar with the images. We know that for the image representation, there are pixels. And also for the 3D model, we could use the voxels. So it's something similar with the images. The image is a 2D grid and the voxel is the 3D grid. So we could analysis and generate the 3D model with the vox grid. So this is a straightforward idea from the 2D deep learning. But for the vox grid, they are usually lack of geometry detail, and they usually use huge memory and take lots of calculation cost. So it is easy to develop the neural network, but it is not convenient for the computer, which would take huge memory and calculation cost. So there are also other approaches, such as using the patches or multi-chats. These ideas also are very popular in the geometry processing. They will use multi-patches. Each patch is a mesh. Use multi-patches to approximate the 3D model, but usually these patches are unstructured and also is not smooth. And also we want, because we know that for the 3D generative model, the difficulty is lying on the structure and the geometry detail. So we could disentangle the geometry and the structure and use the generative model to generate the structure and the geometry in the separate way. So there are other methods such as the using the boxes. Use the boxes to represent the structure. So we will talk something about how to use the structure, to use the box structure to represent the geometry structure, and also how to use the simple boxes to approximate the geometry details in the fine way. And also, as we mentioned before, for the 3D models, one important property for the visual quality is texture. So if we could modeling the texture, the generative model would be much vivid. So there is also some previous method to generate the texture model to enhance the visual quality. One way is that, as we mentioned in the last slide, we could use the point cloud to represent the 3D model. So we also could use the point with colors to represent the textured 3D model. For each point cloud, for each point in the point cloud, we could define the color on the point. So this is one way, but we could think about this because the point is sparse. So although the point with the color, but also the whole model is not smooth and not compact. So it's not an easy way to generate the very high quality visual quality 3D model. And the other the pioneer work is to using the texture field. It's something like the implicit field and to define the colors in the implicit field. But it's not easy way to it's not an easy way to represent the very fine texture. So, and based on the previous work, we could use the cubes, also use the boxes to represent the 3D model, and then we could open the cube. If we open the cube, we could get 6 faces, and this is a very natural way to define the texture domain. So this is one way to do the parameterization. And then we could also define the texture on this cube and also on the 3D model. This is something straightforward from the texturing, but something new for the deep generative model. So okay, I think Michael give some very brief introduction of these 3 works. Now let's go into each work. The first work is the automatic impaired shift deformation transfer. The task of this work is to reuse the deformation from the source model to the task model, to the target model. Like this video in this slide, So if we give the deformation of the female is walking, and we want to reuse the deformation of the female and transform the deformation of the female to the Asmo-like robot. We know that in the previous the sort of works, they could do this task by the label the correspondence between the vertices between the female model and the Asmo-like robot. So they could do the to label the correspondence for each vertices and then to transform the deformation gradient. They need this method needs a lot of human effort, but in this research paper, we want to develop something with the help of the neural network. We want to do this task in the automatic manner without any human effort. So if we want to finish this task with the network, we need this component. One thing is how we represent the 3D model. We could not use the position of the point. This is not easy way to encode and analyze the complex structure. So we could not use the vertices position directly. We need something that we need some representation that is suitable to analysis the complex motion. This is one thing. We need something to represent the 3D different motion. And this is the repetition. We also apply the repetition. Not only we represent the deformation, also we could use this repetition to represent the geometry details. This is something very important in the whole research works. The deformation could also be applied to some general tasks. This is what we would talk in the next work. And here we need some repetition. I will give some slides to talk about the repetition. And given the repetition, we need analysis the motion. We need something to encode and decode the deformation. If we could decode the deformation, we have some tool for the generative model. And if we have the generative model, we could generate the motion. We need to generate some meaningful motion that is corresponding to the given sources. So here we need to develop something like cycle gun. We name it VAE cycle gun. We need to develop some cycle gun. We know that the cycle gun could do the transfer, also very famous work in the image processing to transfer the styles in the unsupervised manner. Here, we share some similar ideas. We use the something like cycle gun to reuse the deformation. The deformation could be viewed something like style, but not the theme. And last, we want to the transformation is meaningful. The transformation should share the same motion. Also, if the female take the right leg and the robot also take the right leg, we need something to supervise the generative result to have the similar motion. Also, this is also in the automatic manner. We need to develop some metric to measure the difference between the target deformed model and the source model. So let's go into the details. Firstly, we need to define some basic tools on the deformable meshes, and we zoom in the meshes. We could find something is the meshes is a combination of lot of triangles, and the deformation of the triangle could be we could use the deformation gradient to represent the deformation of each triangle. And here, let's look at it. We find that from the left triangle collection and the right triangle collection, there are deformation, and we could apply a deformation gradient matrix t, and we could the deformation could be represented by the deformation gradient matrix T. So in each varying grade of the message, we could use the deformation gradient matrix, which is 3 multiplied 3 matrix, to represent the deformation. So given the two deformed given two deformed message in each varying neighborhood, we could get the deformation gradient. This is something straight from the previous literature. And if we view the deformation gradient T, there are two things inside the deformation gradient. One thing is about rotation, and one thing is about the scaling. So we could use the polar decomposition to decompose these two matrix out. So this is all the very state of art things from the previous literature. But one thing challenge is that we know there is some ambiguous, because look at the rotation matrix. Given the same rotation matrix, there may be many solutions for the same rotation matrix. The rotation axis and the rotation angle, there would be multiple solutions. So there are the multiple rotation axis and the multiple rotation angle for the same rotation matrix. So this is something very challenging, also something very difficult to represent the large scale deformation. We know that for the human motion, if the human is dancing, the legs may be rotated with the larger scale manner, and the people also rotate multiple times. So this it's not easy to get the exact rotation angle and the rotation axis of each rotation matrix. So here, the key idea of this representation, we want to locate the exact rotation angle and the rotation axis. So this is the possible solution. Given the same rotation matrix, there are multiple solutions for the rotation axis and the rotation angle. The rotation axis is two directions, and also the rotation angle with the multiple cycles. The task is to identify the unique image of the rotation matrix. So this is the key idea for this deformation representation. This deformation representation is to identify the unique image of the rotation angle and the rotation axis. This is suitable for very large scale deformation. For the small deformation, it is not necessary to identify the unique image, because we can use the something to get it. But for the large scale, we need some optimization to identify the unique image. So the key idea of the method is here. Although there are multiple rotation cycles or multiple rotation direction, we could use the optimization to optimize the rotation axis and the rotation angle. The key idea is that the difference between the axis and the rotation angle of the adjacent vertices should be quite small. So we add the difference between all adjacent vertices. We need the sum of all the edges, the difference between the rotation axis and the difference between the rotation angle should be as small as possible. In another way, we could say that the rotation should be as consistent as possible. So the rotation should, the angle between the rotation axis should be small. So here we use the formulation to make the rotation axis to be as consistent as possible to make the difference between them to be as small as possible. So with this optimization, we could calculate the rotation axis, and then given the rotation axis, we could optimize the rotation angle. The difference between the adjacent vertices, the rotation angle should also be as small as possible. So here we use this rotation the difference between the rotation angle. So we could optimize this formulation to get the rotation cycle of each angle. So here, after these two optimization, we could get the unique image of the rotation matrix. We could get the unique rotation axis and the rotation angle. So here we get one representation. For each deformed model, we could get the rotation angle and the rotation axis for each varying neighborhood, or exactly each vertex. The vertex is the center of the varying neighborhood. And next, given this representation, we want to encode the deformation. So here we need something such as the convolutional neural network to encode to analysis the 3D model. Different from the 2D images, because the 2D images is very regular. We could use some filter or some window to do the convolution. But for the 3D meshes, it's not a very easy task. But with the help of the graph convolution, we could view the 3D triangle meshes as the graph. So each vertex could be viewed as the node, and the edge could be the edge of the vertices also be the edge of the could be viewed as the edge of the graph. So here we could use the some convolution graph neural network to encode the deformation representation. What we have discussed in the last slide, the deformation representation for each varying neighborhood is the rotation axis and the rotation angle. For the rotation axis and the rotation angle, we will do the graph convolution. Here is the formulation of the graph convolution. We will use the weight multiplied with the value in each vertex. The value is the rotation axis, and the rotation angle is the we say this as the input feature vector of SI. This is the to represent the deformation in each varying neighborhood, and this will be multiplied by the weight matrix, and then we will also use the average of the varying neighborhood. It will be divided by the degree of each vertex, also multiplied another weight matrix, and then we also add a bias. This is the convolution operation in each in the mesh level. So given this formulation, we know how we do the convolution on the mesh, and given the deformation representation, we know how we to represent the 3D meshes. So given these two basic tools, we could to analyze the 3D deformation. So next we will introduce some network, the convolutional mesh variational autoencoder to encode and decode the mesh motion. So look at this finger. This is the architecture of the convolutional mesh variational autoencoder. Here we use the generative model. The generative model is the variational autoencoder. We know that the variational autoencoder is not very good for the image generative task. For the image generative task, we usually use the GAN, the GAN network. But for the 3D models, we prefer the variational autoencoder. There are some reasons. One reason is that it's not so difficult for the VAE to train the VAE because it's very difficult. Because the data set of the 3D models is not usually such large. For the GAN, they usually need lots of training data, and the 3D data is usually very sparse and not so much. So this is one reason we use the variational autoencoder. Another reason is that if we look at the deformations or look at the geometry details of the mesh model, is not so sharp as the images. For the images, the distribution of the images is usually very sharp. The difference between the adjacent pixels, it may be very large, but for the vertices, the difference from the adjacent vertices is not so large. So there is something behind the 3D model is the smoothness. So with these two reasons, we prefer the autoencoder, the variational autoencoder, the VAE, to encode and generate the 3D model. So here is the architecture. Given the 3D model, we could use the deformation repetition we just talked before to calculate the deformation repetition, and then we will use the convolutional layer to do the convolution on the mesh model. After two convolution layer, we will reshape the feature into a much larger vector, and then we do the full connection to the variance and mean. This is the architecture of the variational autoencoder. So the decoder is the reflective design of the encode network. So if we want to train this network, we need to define the laws. There are three losses. One loss is that given one shape, if we encode the shape, we want to decode the shape is the same with the input. This is the Reconstruction Laws. So we will measure the difference between the input feature vector and the output feature vector. We need to make the difference to as small as possible. So there is the L2 norm to measure the difference between the encode and decode feature vector. Another very important thing is the KL diversity. Here for the VAE, because the VAE want to do the sampling of the Gaussian distribution, all the input data will be formulated to the Gaussian distribution, and if we want to the generative, we could sample on the Gaussian distribution, then we could do the generative. So the very important thing is that we need to map the input feature vector to the Gaussian distribution. So here the KL diversity is used to measure the distribution of the input model between the input model and the Gaussian distribution. So we use the KL diversity to make the input distribution to be close to the Gaussian distribution, and then we could do the sampling of the Gaussian distribution to do the generative task. So given the loss, given the network design, we could training the network. Also, we could do the generative task. One challenge for the generative task is that some neural network may just memorize the input model. So all the generative model is something same with the input. So they just do the memorize. It's not good to generalize to the new shape. So here we want to test if this generative model is overfitting. So we do the sampling on the Gaussian distribution and decode it. We could get some a new model. This is the thing from the generative model. And then we would do the retrieval to retrieve the training data set to see if it is the same. If it is the same, so this network is overfitting, so it's not a good generative model. And if we look at the figure, we find that the generative 3D model is different from the nearest model in the training data set. This means that this network is not overfitting and could be generalized to the task for the generative model. So we have with this tool, we have get a network that could learn the deformation and generative the deformation with the deformation representation, with the convolution, also with the variational autoencoder. Now, with these three technical components, we could encode the deformation. Also, we could decode the deformation. And this is very basic for the next task. And the main concept of this task is to transform the deformation in the automatic manner. We see that we would use something like cycle gun. The cycle gun could to transform the style in the unsupervised manner, but the cycle gun is defined on the images. So here, we inspired of this cycle gun, we need to develop some suitable network for the motion transfer. So look at the network design. So here, the first row is the variational autoencoder for the source meshes. And the second row is the variational autoencoder for the target meshes. And we will do the mapping on the latent code between the source meshes and target meshes. So the deformation transfer has been formulated to define the mapping between the source latent code to the target latent code. So the very important thing is to learn the function G and the function F. There are two mappings. The mapping from the source latent code to the target latent code, and from the target latent code to the source latent code. This is the this is the key design. The deformation between the source shape to the target shape has been formulated to calculate the mapping from the source latent code to the target latent code. So there are also some discriminators because this here is the GAN network design. We need the discriminator to ensure the to ensure the mapping is right. So let us look at this figure. This figure about something about the cycle consistency. The cycle consistency is quite helpful for the unsupervised design. If we want to do something in the unsupervised manner, we need some loss. This loss is helpful to reduce the human effort. So the very important loss is the cycle consistency loss. Given the source shape with the G function, we could map to the target shape. And then we use the F function, we could also go back to the source shape. So the two source shapes, the difference between the two source shapes should be very small. Actually they should be zero. Because from the source to the target and go back, the difference should be as small as possible. This is the cycle consistency. And also in another view, from the target to source, with the f function and also go back to the target domain, the difference between the two targets should also be as small as possible. Here we define this loss as the cycle loss. It's the formulation is located in this equation. They are actually to apply two functions. Given the source latent code, after the J function, we have gone into the target place and go back with the F function. The difference, if we go back, the difference with the go back position and the source shape should be small. And also in another direction, with the F function, the target position the target code should go into the source code. And also with the J function, they will go back to the target position. And the difference between these two code should also be small. So this with this concept, we could define these two formulation. So this is the cycle loss. This is also something to the similar thing with the cycle gain. Another very different thing is that given the source shape, the source latent code, each source latent code corresponding to each 3D source shape. Given each source shape or the source latent code, with the J function, we could get the target latent code or target deformed shape. And here, we need a discriminator to ensure the transformed shape should be correct. So here is a discriminator network to discriminate the decoded shapes. So this is very important to the discriminator to ensure the function J is all right. So let's go back the overview of the architecture. If given the target shape after the encode and decode and with the discriminator, because it is already existed. So after the encoder decoder, the discriminator would view this sample as true or real. But for the transformed shapes or for the deformed shapes, it would be viewed as fake. Here, let's look at the network design. For the discriminator is the convolutional neural network. The convolutional layer is the network we have discussed before. And for the function G and the function F is the fully connected network because it's very compact. It's very compact code. We should use the fully connected layer to link the source shape, source latent code and the target latent code. And here is the gain loss. And another important thing is that we want the transformed shape should be as visual same as possible. Here we need some visual similarity loss. And one very robust similarity loss is the LSD. It is robust and it is accuracy. But in this work, it has been done about 3 years before. So in that case, there is no differential renderer. So we need to design something that is robust, it is accuracy, and it is also differentiable. So here we design a network. The input is the two shapes. The output is the light field distance. We know that the light field distance is used to measure the difference visual difference between the source shape and the target shape. And here is the regression. So given the two input latent code, we could regress the difference between the latent code to the VCO difference. And here, this network will be used to measure the difference between the decoded shape. And this is quite helpful for the unsupervised learning because we use some network to learn the VCO similarity. So we could also look at this figure. We find that this VCO similarity net is very helpful to measure the difference between the input two shapes. Given this horse and given this camel, we could use the VCO similarity net to measure the difference, and this network is trained well of the data set. And here is all the losses. We for training this automatic deformation transfer, we need the similarity loss, we need the cycle loss, and we need the gain loss. So we sum them together and to with some weighting, and then to use this loss to train the neural network. And after this, after the training, we could do the automatic deformation transfer. And also we could use some human effort because we could change the VCO similarity loss to some human labeled pair. So this method could also be extended to the human labeling, but it could be also be worked in the automatic or in the unsupervised manner. Now let's look at the evaluation and the result. So this is the published study of each loss. We could find, and each loss is quite important for this task. With all the losses, the input shape, the deformation of the input shape could be transformed to the target shape. So we could find that the transformed result is very close to the ground truth. And also, we do some evaluation of our training strategies. We find that this network is not so easy for this network to train in the end-to-end manner. If we do the separate training, the result is much better. And also, we compare our method to some pioneer work. The pioneer work needs the human labeled. We could see the figure that the traditional method needs the correspondence of the thin people to the fat people. They are very from the source correspondence to the dense correspondence. The source correspondence is 15 manually labeled landmarks between the source shape and the target shape, and the dense one is the 40 manually labeled landmarks. So there is many much human labor effort to label this correspondence of this marker. And let us look at the result. And we find that our automatic manner, our automatic deformation transfer method could transfer the deformation in much meaningful manner, because look at the rightmost result is our result, and our result is much better than other methods. Although this method is with human effort, but with this network design, we could get much better deformation transfer result. And here we introduce something about the automatic transfer, and also the deformation could also be used to generative some other things. Not only the deformation mesh models also could be applied to generative some man-made object. So here we will talk some much general mesh models about the 3D man-made object, and also we could apply the same technique from the deformation repetition to the general man-made object. So let's look at the man-made object. We can find that the man-made object is equipped with such things is equipped with the sharp details and also equipped with the complex structure and also with the texture. So it's not an easy task for the deep learning to represent this deformation. If we use some workload, the workload could not represent the fine geometry details. It is good that we have developed some representation for the motion. Could we apply the deformation representation to the man-made object? So this is the key idea of this research work. Look at this figure. We get some inspired from the mathematicians, because from the mathematicians we can look at this figure. The cup could be deformed as from the cycle. From the cycle, we could deform the cycle to the cup. We could use the deformation to deform some basic template to approximate the fine geometry details. So here is the key concept. We could use the deformation to approximate the fine geometry detail of man-made object. So here we could use some technique developed before, and also we could to represent the fine geometry detail of a man-made object. But different from the human motions, we know that all the structure of the humans is almost the same. So the vortex connectivity between the humans is also the same. So the structure, we do not pay much attention of the structure of the humans. But for the man-made objects, we need something new to handle this complex structure. So here we use some straightforward graph structure to encode the structure of the man-made object. This is some work about finished two years ago, and recent years also me and Jie also together with Katrin, we have developed some much better structure to represent the very complex man-made object. But this is some initial solution. So here with this geometry representation and with this structural representation, we could generate the 3D mesh model. And look at this figure, we can find that the generated the 3D mesh model is with high visual quality. The geometry detail is very fine, and also the mesh is smooth. Another very good thing is that because it is a mesh model, we could apply the editing on the meshes directly. We could use the editing technique to deform the chair to modeling some new shapes. So this is the benefit from the deformation representation. It gives some suitable representation for the deep learning. It could represent the geometry detail well, and also it could easily for the user to re-edit the 3D shapes. So here, let's look at the technique component of this method. This is something from the previous deformation representation. Here, given one 3D man-made object, we need to do the segmentation. Given the segmentation, we could using the bounding box to cover each segment path. And this bounding box defines a template. And then we could apply the non-rigid registration to deform the template, to approximate the target geometry. So here we deform the cube, and after the deformation, the cube looks like the input shape. So with this operation, we get some a very good thing for the deep learning, because the cube or the template or the exactly the bounding box shares the same vertex connectivity, and the position has been deformed to the input part. So now we have get a new part. The new part shares the same vertex connectivity to the cube and also shares the geometry to the input part. So it looks the same, but with different vertex activity. And because the cube is the template, so we could apply the graph convolution as we mentioned before on the cube. So here we could use this variational autoencoder to encode the deformation. And now the deformation is the geometry detail, they are equal. So here we could use the very convolutional VAE to encode and generative the deformation. Here is the geometry detail. And look at this slide, given one cube, we could use the one cube to represent the very diversity 3D model. And here the technique, the idea is borrowed from the deformation repetition. The left is the deformation. We could deform the template shape to the, we use the cube as the template, and then we apply the deformation on the cube. Then we could get the visual similarity shaped with the input segment, but with the same vertex connectivity with the bounding box. And also we use the convolution layer we had discussed before. And this is the geometry encoder decoder of each part. They are very similar with the convolutional variational encoder, variational autoencoder for the deformation. And here with this technique, we could generate the geometry detail from the each part. But there is also something not so easy to handle, because not only the geometry detail, with this technique we could generate the geometry details, but there are also structures for the 3D model. If we generate the parts separately and look at the left finger, the whole shape is not meaningful. If we because we can look at the left finger, it's not a meaningful model. The only with the adjacent relation is not enough. However, we have introduced some structure about the graph structure to reflect the relation. So here we use the supported relation to model the adjacent relation of the 3D model. We know that we use the graph structure to encode the shape, and the edges of the graph is used to encode the supported relation. What is the supported relation? Is from this we could look at this plane. So let us look at this plane. There are several parts, and from the plane, from the ground to the top, there are a supported relation. So given this plane, we could firstly do the segment, and we could get each segmented part, and then we from the adjacent relation, we could build an undirected adjacent graph, and then we would analyze this relation. We could find the support relation, and then we could get a directed support relation. And this supported relation will used to modeling the structure. And now we have encode all the information of the 3D model about the geometry detail. The geometry detail is the deformation here. And also the structure has been modeled as the support graph. So given each model, we could do the support analysis and do the deformation approximate. And then we should analyze the symmetry. And then given each shape, we could get this code. This code is used to encode the input shape, including the existence, the supporting relation. The part is supporting which part, and this part is supported by which part. Also, something about the geometry, some information of geometry. The center of the geometry, is it existence of the symmetry, the parameter of the symmetry plane, and also the geometry detail. The geometry detail is the deformation detail. The deformation detail, we could use the variation autoencoder to encode the geometry detail to get the encoded vector of the VE. Here we call this V, we name this V as the part VE. And then given each shape, we could get a vector. The vector encodes the graph relation, the support relation, and also the geometry detail of each shape, and put all the shapes in the variation autoencoder. We could training a structured path VE. We put all the shapes, we take the shape, we analyze the shape, analysis the deformation, analysis the structure, we get the code, and we put all the code into the network. We could train a generative model. And also with the graph structure, we could also do some post-processing to help to make the model in much reasonable way. So look at this finger. Because with the because we encode the geometry details and encode the structure together, we could generative the model in much reasonable manner, like the rightmost figure. If we generative the models in the very decoupled way of the model, the structure and the geometry may not be consistent. So look at the rightmost finger, the geometry and the structure are encoded in the separate manner. So the decoded shape, without talking between each other, the decoded shape is not consistent because the geometry and the structure is not consistent. If we do them together, we could generate some meaningful mesh model. There is another problem is that for the generated mesh model, the geometry detail is fine. Look at this finger. The geometry detail is fine, but the structure may not good. And however, because of the generated code, including the supporting information and the supported information, we could use the information to refine the generated shapes. So we could do the refinement given the decoded supported relation, because we have encoded the supported relation, and also we could decode the supported relation. The supported relation would be used to do the shape refinement. So here is the optimization. Given the decoded shape code, we will do some post-processing. We want to move the path, and to move the path to recite the path to make it to adjacent each other, also to support the path in the stable manner. Because look at this thing, this 2D example. It is also generated path, but they are not stable, supporting each other. They are not stable. So we need to optimize the size, the length of the legs, also optimize the position of the legs, also optimize the position of the tables to make them consistent. And most importantly, that is to make them after the optimization, each part should be stable. So here we given the decoded supporting information, we could optimize the position, optimize the size to make the parts to support each other in the stable way. So look at this result after the refinement, we could get the much meaningful and much reasonable man-made generated model. And also this method could be generalized to other models because given the new shapes, we could use some very famous segmentation method such as pointnet plus to do the segment, and then we could use the method we discussed before to encode the input shape. In fact, after the segmentation, we could encode each part, and each part geometry could be viewed as the deformation, and the relation between these parts could be used the supporting graph to represent. So here we do this experiment on this set. Here is the result and comparison of other generative model. We can find that with this technique, we could encode the shape and decode the shape in much fine manner. The geometry detail could be decoded much well. Could look at this geometry detail. It's much better from compared with some other generative model. The video shows that given the input shape, we could reconstruct, decode the shape very similar with the input shape, and with other method is not so easy task because the other method may depend on the worksource. The worksource is not easy to represent the geometry detail, and also we could do the shape interpolation on the latent code. Given this shape, we could do the shape interpolation. It's very smooth, and each shape is also meaningful. And here, this slide demonstrates the generated meshes. We also do the comparison of other generative models. We could find that this method could generative models with fine geometry detailed, and the generated shape could support each part in the stable way. And here are some numerical metrics. We can find that with this repetition, the travel distance loss and the other also the EMD loss is EMD distance is much smaller than other method. And as we mentioned before, if we want to modeling the 3D shape with high visual quality, they need the fine geometry detail, they need the complex structure, and also need the texture. And given these approaches with the boxes and also with the deformation representations, we could define a very natural way to encode the texture. So here we will talk about some deep generative network for textured meshes. So for the textured meshes, without neural network, only considering texture, the most texturing approaches is to decompose the mesh into parts and each part is corresponding to images. Is something we call the UV mapping. We need to decompose the shape into patches and do the UV mapping of the mesh patches to the image domain. So this is very common for the industrial, also for the texture mapping. We call it texture mapping, but for the generative model, it's not so common. If we want to get the high visual quality mesh model, we should borrow some idea from the text mapping. But the text mapping is not easy task. It's not easy to map a complex 3D mesh model to a basic domain. It's a very, very difficult task because the shape of the 3D model is very diverse. So it's not an easy task to map the 3D model to a basic domain. However, with the help of the previous method, we could define this UV mapping in much friendly manner. Look at this figure. The key insight is that with the box structure, we could decompose the complex models into boxes. And for each box, if we open the box, we could get an image. This image, like as the left finger, the opened box with 3 patches. This operation defined a UV mapping from the 3D textured mesh path to the 2D images. It's a very natural way to define the mapping, but it's not very easy task for generate 3D model. If we firstly we decompose the 3D model into each part, and then we open the box, we could define the texture mapping. And this operation defines very good domain for the deep learning, because we know that for the deep learning we need to align all the data set. For the images, it is easy task, but for the 3D model, it's very difficult. So here we decompose the 3D model into each part and open each box. We could get a pad, get an image, and this operation defines the UV mapping. And also there is some challenge to represent the complex structure, but with the help of the texture, there is some trick. We could use the alpha channel, the transparency, to model the hole. Look at the right chair. We use the alpha channel to define the transparency, and with the transparency, although this part is watertight, but with the help of the transparency, we could view some hole. So this is a trick to represent the complex hole or complex topology, but this is not actually solved it, but with some trick we could generate some model with the complex topology. So here let's review the technique. For the geometry details, this is the same thing from the part VAE. We could use the same technique of the part VAE to encode the geometry detail of the input shapes. Another very important thing is that with the solution, we could decompose the input shape into parts, and with each part we open the path, we could define the UV mapping, and in each UV mapping we need a neural network we need to design a new neural network to encode the texture of the meshes. The texture is very challenging. It's very challenging for deep learning because it's a very high frequency. It's very high frequency, so it's not easy way to learn. So the way would be failed. We need some other some other encoder. Here we use the VQVAE, the vector quantification VAE, to encode the high frequency texture. The input texture not only include the RGB channel, also includes the alpha channel. The alpha channel is used to represent to encode the transparency. The transparency is used to represent the whole, the structure. And also we use this VQVAE to encode the texture. Here is we also need to make the consistency, to make the smoothness between the each patches, because if we close these patches, it will become a box. If become box, the difference between the boundaries should be as small as possible. So we encode and decode. The texture in the 2D domain, but we need to do the visualization in the 3D space. So in the 3D space, we need the difference between the 2D boundaries should be as small as possible. Here we will involve this loss. And then with this texture encoding component, we want to do a mapping. The mapping is between the geometry to the texture. Given a black 3D mesh model, we want to texturing this. We want to do the texture on the mesh model. So here we need to design some autoregressive model. Why we use the autoregressive model is that usually there is one geometry corresponding to multiple textures. Look at the card. Given the card geometry, there are usually black card, white card, and red card. So we need to learn the one-to-many mapping. So here we use the autoregressive model for the texture generation. Now let's look at the results and evaluation. With this alpha channel, also with the transparency, for the black model, we could to encode the whole. This is very different from the we have talked before, the SDM net. We could use the texture to handle the complex structure, and also we could encode and decode the textured meshes, and also we could do the textured mesh generation, and we could do the sampling, and with the autoregressive model, we could do the model generative, do the generative model, and also we do the comparison of other methods. We could find that this approach could generate much better texture. And also the leftmost model, if the input model is given a black model, we could do the automatic texturing of the three black model with the meaningful texture. For the table, the chair, or for the card, we could texture the input shapes. And also we do the comparison with the text field. We could find that the TMNet could generate much fine geometry, fine texture. But it's not an easy task for the interpolation, and we find that the limitation of this TM data is that the learned shape written code is not so compact. If we do the interpolation, the interpolated shape has some artifact with cross feeding, so it is not easy for this network to do the textured shape interpolation. So here, let's do the summary. we developed a deformation representation, and this deformation representation had been applied for some deformation transfer task. And also with this deformation representation, we apply this deformation representation to man-made object to represent the geometry detail of a man-made object, and developed the SDM net to generate the structure and geometry detail. And also with this SDM net, with the structured deformable mesh model, we developed the texture technique to texture these man-made objects. So this is the core works. And also there are some limitation of future work. We can find that for the SDM net or TMNet, they relied on the segmentation. It would be much better to discover the shape structure in the unsupervised manner. This is something we expect to explore in the future. So this is the pipeline of all the and the relation of all the work. And thanks for the audience, and thanks for my students and the collaborators on these works. And thanks a lot again. So my talk has been finished.
Okay, so thank you, Professor Gao, for that very interesting talk. So we've actually covered quite a bit of ground and gained some, I think, deep understanding into handling 3D models, especially 3D mesh models using generative models. So at the moment, I would like to again welcome our panelists, Yili and Mo Kai-chun, and maybe give the floor to you guys to see what you guys would like to discuss after this talk.
Okay, thanks. Yeah, actually, thanks, Professor Gao, for this nice talk. You covered a lot of topics, also very relevant to like my research, Kai-chun's research. So I think this is a very interesting area, especially when you're considering modeling the deformation. So right now, most of the works you covered is targeting at object and also mesh, right? So it's like quite curious, what is the gap between kind of bridging this technique with say analysis or understanding of natural scans, maybe just point cloud data? Do you think it's like a very difficult thing to do, or like because you have a lot of assumptions about how you develop mesh VAE, how you use like mesh deformation representations? Like, what if we want to handle sometimes like the partial scans captured from the real world? You want to consider this motion transfer or texture transfer type of problem. Firstly, do you think this is a valid problem setting? Secondly, do you think the technique could be very different or quite similar?
Yeah, very good challenge, very good question, and then also very challenging for this technique to apply this technique to the real scan, because the real world scan is usually lacking the correspondence from each other. I think the most challenging thing is to build the correspondence. If we have the correspondence, and these techniques could be applied directly, because all the real world scan could be viewed is decomposed of each part, and given the correspondence, we could given the correspondence, we could decompose the real scan into each part, and if we could decompose the real world scan into each part, we could bring these techniques back to the real world scan. So I think the gap between the real world scan of these regular solutions is the gap, or the bridge is we need to develop some robust computer vision tools to build the correspondence in the robust and in the accuracy manner. So this may be the future works in the next.
Yeah, thanks. like a follow-up questions, you also mentioned like this probably needs more fancy computer vision techniques to build more robust correspondences between real scans. Another kind of relevant question is now we talk about generative models from different aspects. Do you think this, because we know like another usage of generative model is to build understanding about the data, could this deformation analysis be helpful for analysis tasks or computer vision or perception tasks in reality?
Yeah, well, I think this is a very good direction, and especially for the maybe not only for the man-made object, for the human emotion. With this generative model, we could make we could make much more training data set, also for learning the vision task. So I think it's a very good idea and a very good direction in the future. But I'm sorry that I have not explored it, but I think this is a potential very good direction in the future.
Yeah, I have some clarification questions, but maybe Kaichen, do you have anything you want to say?
Yeah, so we are starting from the high level question and then the clarification question. So if so, I think yeah. So I have a maybe mid-level questions because I think so. First of all, thanks for the nice talk. But I think there's maybe a limitation of this method because you are deforming a source mesh, a template mesh to the target mesh. So here you're assuming like the underlying topology are the same for two mesh. Right? So how about for some details that the topology will be different? Yeah.
This is a yes, this is a limitation of this already existed approaches. So this also made me to think more about this. So we also have some effort to try to solve this challenge. One thing that like the TMNet, we add some texture. So although they develop the template, we could add some operation. Because this like something like the topology operation. Given the texture image, we could define the hole, and if we define the hole, we could remove these pieces. So they will divide into two steps. One step is to do the deform, and the second step to do the topology operation. The topology operation is guided with the images. So this is one way, and another straightforward way, I think we could divide the shape into much basic element. If we divide enough, that we don't worry something because we need to just to deform each basic element, and I think you said something could be completed with the structure operation because we have divided enough. But maybe this not these two these two methods is not good enough. We could explore more some representation. The deformation is something like mapping. Also, the deformation is to do the mapping from the source domain to the target domain. We could change the representation, not use the deformation representation, also use some implicit field or something like some novel representation to do the deformation, not the deformation on the mesh vertices, but to do the deformation on something, maybe do something on the implicit field. I think this is the open question. So we may think together, in the next.
Yeah. Yeah, thanks for the answer. So actually, I'm going to ask about the implicit function. Yeah, because in your talk, all of the projects are conducted on the explicit meshes. So of course, the advantage is that we directly get a mesh, so that it's easy for us to render, to manipulate, to edit. But yeah, so you should also know that the recent popularity of the nerve-based method or implicit neural things. So their advantages is that they don't have the limitation of the topology, and the nerve work can also learn from real images, so they can infer the realistic texture. So how do you compare like the implicit representations and explicit ones for 3D representation?
Yeah, I think for different man-made objects, the different representation has its own advantages. For the man-made object, so this is I will talk about later. For human bodies, the deformation representation is much better, I'm sure, because the deformation representation could handle very large scale deformation and very detailed geometry. It is all right. So for the human body motion, so the deformation representation is good. But for the man-made object, we know that the nerve or implicit field is free of the topology and it is better from free from topology. But the very challenging thing is that it's not easy for the implicit field to model the sharp features, although we see something. And also it's very difficult thing for the deformation representation to represent a very sharp feature. And also current representation, current solution of the implicit field is not, the resolution is not very high, because if we want to modeling the very detailed 3D models, the implicit field method is also not enough. So I think if we want to generate the very fine geometry with a very free topology, maybe these two methods it still need some much more effort to do. So I think there is not actually some very good method to handle all kinds of 3D meshes. So each method, each representation has its own advantage and disadvantage.
Mhm.
A relevant
Yeah, thanks.
question is, have you think about like designing those constraints for implicit representations? Because for meshes, we can have as rigid as possible constraints or as consistent as possible constraints. Is it easy to design something similar for implicit representation? Have you thought about that before?
I think this idea is quite smart or quite good. So I have some initial idea, but I don't know how to modeling the mathematics to use the as rigid as possible energy or something like that to on the implicit field. Because the most difficult thing for the implicit field is that although we have get some good implicit field, it's not easy because we have to use something such as matching cube or something with this will make the mesh not good. So I think it's a very good thing to define some energy to some constraint on the matching cube method. I also see some very good work from the Professor Richard. I see a very good matching cube method to define the sharp feature. I also think this may be the future very good direction to solve this problem, because the implicit field is also good at it's free to topology. It could handle memory object, but with after the matching cube, the shape would become worse, I think. So add the constraint on the matching cube or use some learning techniques to make the matching cube to keep the sharp feature or to learn some smoothness. It's a very good direction. Although I'm sorry, I have some very initial ideas, but I don't know how to model it. This may be very good future work.
Yeah, thanks.
Maybe we can take a few questions from the audience at this moment. So I'm going to also type them into the chat just for your reference. So from Hong Yingling, she was wondering, this person is wondering basically that for the SDMnet work, how you actually decide which template mesh to deform from. So I think from your previous discussion, if I've understood correctly, you're basically assuming that this template mesh is already known, right? And
they want to know how to define the template mesh, because given the for the data set, for the legs, for the chairs, for the table, there are meaningful semantic segmentation. So the meaningful segmentation will define the templates. We will segment the shapes with the semantic labels. So this defines the structural template.
I see. So then you make some assumptions based on the segmentations that the closest matching template should be either some cube or some rectangular block or so on, right?
Yes, although it's not cube, we could after the segmentation we could calculate the bounding box. Maybe it's not a cube, we could calculate the bounding box and then use the bounding box as the template to do the registration or deformation.
I see, I see. Okay. So there's some other questions from the audience also from Cong Yu, who asks, let me just paste the question here also for you, is to ask if the ACAP deformation is robust to either resampling or remeshing, either in some theoretical way or an experimental way. And specifically, they were asking that in the shape reconstruction experiments, is the output shape in the same mesh as the input, or if the same shape is actually remeshed?
It's remeshed. It's remeshed with the topology, with the template or the bounding box. It has the decoded shape or the encoded shape as after a transformation. The transformation will do the remesh because the geometry looks the same, but the topology has been changed. It has been changed into the template bounding box. So for the ACAP feature, I think the ACAP feature or as rigid as possible, deformation is in somewhat is robust to the remeshing because there are some technique from the weight. The weight is the because for the energy there the weight is robust to the meshing. So if the mesh is good with manifold without non-manifold edges, so this mesh works. For each edge, there should be adjacent with 2 faces, not 3 faces, and there is no only one vertex with maybe so there is a manifold deformation. I think there is a definition from the manifold. If the mesh is the manifold, so the ACAP works. So I think most of the meshes it works, and that it is robust, and also the code is released. Can have a try.
Okay, great. So then following up on that point, the question is basically within the generative model, this network output, this is a 3 times V tensor, right? So V, I guess, is the number of vertices. So the question here is then, how are these output vertices, are they ordered or not? And whether you maintain some sort of coherence between the input or output, especially because within the network, there are some flattening layers, right? That might potentially disrupt this ordering.
Yeah, it's ordering. It's because the order of the input or up I think the input could be divided into two models. One input is the something from the data set is the one input, and another input is after the representation, after the deformation representation is another input for the input of the neural network. For the input of the neural network and the output of the neural network, the order of the vertices is the same. But it doesn't matter. Yeah.
You have to maintain the structure throughout.
Yeah.
Okay, makes sense. So we have another question from Xiaolong in the audience who says, thanks for the nice talk. And he's is asking with SDMnet, whether it's possible to remove this shape refinement network. So you want to preserve the connections, but at the same time allow some deformations as well.
Yeah, I think this something. Yeah, actually, we have done something. I think in the DSDNet, they work in this idea because in the SDMnet, they predict the geometry of each part, and we need the post-processing to fuse the parts together. This is the idea from the SDMnet. But we could also modeling the relation between each part in another method. We could model the relation of each path, and because the network is predictable, the path from the input output after the neural network, they could predict each path, and they are not guaranteed to make sure each path to connect with each other. So this is something from the neural network, because from the input output is the forward path. But if we want to fuse them together, like this question, we need to the network, the structure design, it should include something. After the forward path, it could decoded some structure to ensure they are connected with each other. But I think the SDMnet is not able to do this. They need to predict these two paths is connected, but they are not guaranteed. After this predict mask, or after this indicates, we could do the post processing to fuse them together. This is what we have done in the SDMnet. But in the DSGNet, they use the hierarchy graph structure. The hierarchy graph structure is very complex to encode this complex structure after the neural network, after forward path of the neural network, the relation of the path has been considered. So in that work, it could after the although without the post processing, with the structure design after the network, we could get some meaningful layout of the path. So I refer to the another under review work, the DSGNet for this question, because in that work, the path is organized in much complex or much reasonable structure with the hierarchy graph to analysis this analysis and decode this structure. So that work could done. This is also something the starting point from the DSGNet.
Okay, thanks. If I can follow up with the question of my own, there is much of the post-processing that we've seen at the moment seems to be concerned with ensuring that these parts are connected with each other, right? I was wondering if you have some thoughts on how we might be able to incorporate some additional physical constraints. So not just the fact that these legs are attached to the table, but that these are realistic such that they suggest that they could support the table, for instance, right? I mean, you slowly get there. I saw in your example with the legs to ensure that the legs are at least the same length. This is a starting point.
Very good, very good direction. I'm sorry that we have not explored more, but I think it's much more meaningful, because just generative model, we need to using the 3D printing to print the 3D model. We need to obtain some physical laws. If it's too thin of the legs, if people sit on the chair, the chair will be broken. So the legs are not so thin. It may be the size is much larger. Also, we add some physical things, but very easy. So we need the center of each part should be located in the boundary of the supporting area. We had added this constraint in the SDMnet, but it's not enough.
Yeah.
I think yeah.
Okay, yeah. So, I mean, you think that this is do you maybe give us some hints for some of the students in the audience, maybe if they're interested in exploring such things, what is a good direction to go down for looking into such a topic then?
Yeah, I'm sorry that I have not thinking deeply about this question, but something come into my mind that we need using some FEM finite element FEM finite element method to analysis the existing methods. We need to the neural network to learn the pattern from the physical simulation, and add some discriminator from the learned from maybe from the FEM method or from some physical simulation method. We training some neural network. We use the
I see.
maybe something.
Okay. Oh, that's interesting. So the topic also becomes much more interdisciplinary then.
Yeah.
If we want to make much more real world considerations also, right? Yeah, thanks for that. Maybe we can go back to our panelists if you guys have any additional questions for Professor Gao. I think from the audience, we're all good.
Yeah, so
Yeah,
if I can
another question from, okay, maybe Kaijun, you'll go first.
Yeah, so I just have a pretty low-level question. So for the ACAP feature, you are using the one-ring neighborhood. So have you considered about to expand into a two-ring or three-ring, and will the technique apply there? Because that will incorporate more neighboring vertices at the information context.
Yeah, thanks, Kaijun. And actually, we have tried multiple rings, and also we published one paper of the one ring, two ring, three ring, much larger part, because the ring is much larger, it would be much rigid. Let's think about the limitation case. The whole shape at the maybe at any ring, the whole shape at the ring, there are only one rigid rotation. So if we make the ring is much larger, the rigidness is much bigger, because maybe the whole shape maybe only one rigidity. So here, but that paper is a more improvement of the as rigid as possible work. We test the multiple rings, but for the A cup rings, we only use the one ring, because here we want to represent the deformation. So we need a much flexible manner, because they already give some deformed shapes. Here we want to learn the pattern. If we want to do the editing, we could add the ring, because we add the ring, we add the rigidity of the part. So here, because we want to learn, we want to the feature to be much flexible. But if we want to do the modeling, we may change the ring, because and also after finish the data research work, I think another way is changing the ring is make the triangle much bigger or simplify the model. If we simplify the model, we get a much larger triangle. It have the same effect of the two ring or some ring. Is something of the discretization, I think.
I see. Thanks. Yeah, I'll pass.
Yeah, like one question from my side is now, especially for the SDNet, like in order to really have the structural understanding, we rely much about the kind of structural supervision, like the PartNet annotations or something similar. So like what would be the direction if you want to really reduce the supervision, but still want to benefit like from the structural understanding, like deformation plus structure, but without that strong supervision? Will that be an interesting direction from your side?
Yeah, I think this is very good direction, and also something we want to explore in the very recent next. And I also think there are also some methods have done some something related, like they use some laws to learn the network from the maybe. I think I have found one very good work from the Professor Su Hao. They use some cubes with only with the transfer distance. They want to the distance to be small and use as less as boxes as small. So with maybe with those two constraints, the box should be as small as possible. The difference between the box and the point cloud should be as small as possible with some heuristic loss. With optimized these loss, we could get some structure. So we need to design some losses. With these losses, we did some design some algorithm to discover the structure. And also I think this may be very difficult. Also, I have not very clear idea at this moment, but I think we can maybe use something borrow from the learning community with some few shot or few shot method, because we can label several several models, not only all the models, because all the models is a huge work. We can label some typical models and transfer the labels to the similarity 3D models. I think maybe in the next the using the few-shot learning is much easier for the shape understanding. Maybe in the final we want to develop some unsupervised discovery method, but this may be not so easy and very challenging and very good direction to explore.
Yeah, totally agree with that. Another maybe relatively high-level question is like from this SDMnet, this texture transfer, most of the topics focusing on objects. How would you imagine, like, if you want to generalize these techniques to model scenes? We know like the relation is much looser, but still we have certain relationships like the support, like the adjacency, this type of thing also appears in natural scenes. Is it possible to define something similar like a deformation space for indoor scenes and then doing something similar? Or have you seen any work related to this already?
Yes, we actually we have done something with things with the deformation repetition with the actually with something to I think also things that there is including detail and the structure. For the details, we could borrow the deformation repetition to handle the man-made object detail, and also for the structure that we could use some structure things like the hierarchy, and also something we have finished one paper, but we have not posted it upon archive. So we already finished one draft and maybe submit that paper to some graphics journal or something.
Oh, that would be great to see what is there in that paper.
We're all looking forward to reading it then.
Thank you. Thank you. Oh, together with Katrin. Yeah, also the joint work with Katrin.
Okay, thanks.
Yeah, that's a good paper. Worth reading.
We're looking forward to it. If I might actually just wrap up for today then. So I'd like to thank Professor Gao and also our panelists, Kai-Chun and Yi for joining us today. It was a really interesting talk and also some stimulating discussion afterwards. And thanks again, guys. I hope everybody in the audience enjoyed as well. And tune in again next week for another talk then.
Thank you.
Thank you very much.
Thanks again.
Thank you.
Bye-bye.
Take care, everybody.
Thank you.
Bye.